Hello, game theorists. Today we are still in chapter 16, looking at auctions. We are in the subsection on all pay auctions. In our previous episode, we looked at what happens when everyone places the same value on the object. So one case that got a lot of curiosity when I taught this class last time was, what if different people place a different value on the object? So it's not in your book, but it's a very interesting question. We will explore it here. A potential question from you guys to address first of all. That question is, could this be on a test? The answer is maybe. So it's not in the book, but we are going over it here. So yeah, could be on the exam. We'll start with the very simplest case. That's when there are just two bidders. So V1 is going to be bidder 1's value. Before, in the earlier episode, everybody had the same value, so you just had V for everybody, but now that the values are different, you have to distinguish them. So you get these subscripts 1 and 2 to indicate that. So V2 is bidder 2's value. So we're going to assume that V1 is greater than V2. Potential objection from the non-existent audience. What if V2 is bigger than V1? Well, it turns out you just pick bidder 1 and bidder 2 in such a way that this is true. So let's say our two bidders are, who are some of our usual volunteers in class? I think Samuel volunteers a lot, and sometimes Rachel volunteers. Let's say Samuel and Rachel are at this auction. So let's say that Samuel has a higher value than Rachel does. Samuel thinks the object's more valuable than Rachel thinks it is. Well, in that case, you just define bidder 1 to be Samuel, the one with the bigger value, and you define bidder 2 to be Rachel, the one with the smaller value. So you can always just pick 1 and 2 in such a way that this becomes true. So there's no loss of the generality of these results when I make this assumption. It's perfectly harmless. So we'll start by looking at bidder 1's problem. So bidder 1's payoff is going to be pi 1. So bidder 1's value is V1, and if he wins, he gets V1 minus B. So you get the value of the object, in your opinion, minus what you had to pay for it. Now, what is the probability that bidder 1 wins? Well, that's going to be P2 of B. So how do I know that? Well, because the bidders have different values, that means they're going to have different probability functions for how they're going to bid. They're going to bid in different ways with different probabilities. So remember, we said earlier that P of X is the probability of bidding less than X. So that means that P2 of B is the probability of bidder 2 bidding below B. So if you're bidding B and they're bidding below B, that means you win. So this is the probability that bidder 1 wins the auction. So that's what they get if they win, and that's how likely it is that they'll win. If they lose, they get a payoff of minus B. Remember, it's an all-pay auction, so you have to pay your bid whether or not you win. It's like a sport where you put an effort to train, that's your bid, that's how much training you do, and you don't get a refund on your training even if you lose. So you pay your bid B if you lose, and the likelihood of losing is going to be 1 minus P2 of B. So where does that come from? Well, if you win with probability, let's say 30%, that means you lose with probability 70%. Or if you win with probability 20%, you lose with probability 80%. In general, if you win with probability P2 of B, you lose with probability 1 minus that. All right, so we found bidder 1's expected payoff. We can simplify a bit. So I'm going to expand this term. So I have V1 times that. And I have minus B2 times, minus B times that. And we expand this, so minus B times 1 is going to be minus B. Minus B times a minus P2 is going to be plus because 2 minuses make a plus. And these guys just cancel out. We've got a minus B P2 and a plus B P2. So we're left with V1 times P2 of B minus B. That's our expected payoff. We want to maximize that. We all know by now the procedure for maximization. That means take the derivative, set that equal to 0. So that's going to be V1 times P2 prime of B. And derivative of B with respect to B is going to be just 1. Set the whole derivative equal to 0, and we're left with that. Now we can do some rearranging to solve for P2 prime of B. So first I'll push that 1 to the other side, and I get that V1 times P2 prime of B equals 1. Let's divide both sides by V1, and we get that P2 prime of B is 1 over V2. So what's the interpretation of what we've got over here? Oh, sorry, I made a mistake. That's a V1, not a V2. All right, now that I fixed the mistake, what's the interpretation as to what we've got over here? Well, remember from our previous episode, we said that the derivative of the function there, of the CDF, is called the PDF, the probability density function. And the way probability density functions work is that the area under them corresponds to the probability. So V1 is just a constant, so this has a constant height of 1 over V1. And where is this end? Well, total probability has to be 1. So if this is going to be flat, we're talking about a rectangle here. So how do I make that rectangle have an area of 1? Well, its height is 1 over V1. The base head better be V1. If that's true, then base times height is going to be 1. Probability is 1 in total, so that checks out. Now, as for person 1, we worked through their problem. It's symmetric, so for bidder 2, you go through the same process, find expected payoff, take derivative, set equal to 0, same process, and you're going to get that P1 prime of B is 1 over V2. So, there's some more, I'll draw a graph first. So it's going to be, because V2 is constant, you have a constant height here, 1 over V2. Now it's a rectangle with height V2, then our base head better be V2, because probability under it has to be equal to 1 in total. So, some more remarks about this problem, because we're not done yet. So, one issue you might notice here, this is not a mistake. One issue is that bidder 1's bidding function depends upon bidder 2's value. That's not a mistake. We know you should never bid above your value. So it means that person 2 should never bid above V2, right? You never want to intentionally overbid. We talked about the winner's curse a bit in an earlier episode, but that only can occur by accident if you're uncertain about values. but you never want to deliberately bid above your value. That never makes any sense. So if bidder 2 is never going to bid above V2, then you don't have to bid above V2 either. It suffices to bid them to outbid them by a single penny. So if their valuation is 50, you have to bid 100. Bidding 51 suffices to beat them. So that's why bidder 1's bid depends upon not their own value, but just trying to outbid person 2. This brings us to another possible objection. So yeah, bidder 1's bidding function depends upon what person 2 is doing. Similar reasoning leads us to bidder 2's bid function depending upon what person 1's value is. But did I just say they should never intentionally overbid? And we said back here that we assume that V1 is bigger than V2. So if V1's over here, then V2's got to be somewhere like there. So if we follow this solution here, that means that bidder 2 is going to sometimes overbid, but we know that can't be right. So how do we deal with that complication? So my class asked me about this. I tried solving my own, but it's pretty difficult stuff. I had to go get some help, and I found a paper that addressed that subject. And here's what they concluded. So the paper is by Hillman and Riley, if you're curious. So our solution for bidder 1 is valid. So bidder 1 is going to bid in this range because V2 is less than V1. Bidder 1 never overbid, so that part's fine. So that part of our solution is correct. So for bidder 2, they show in their paper, and it's rather complicated, so just trust me on this one. They should bid 0 with the following probability. And they bid 0 with probability 1 minus V2 over V1. So with the other probability, with probability V2 over V1, you're going to bid according to the rule we had earlier, which was that P2 prime of B was 1 over V2. So here's the idea for what is going on here. So we showed earlier that this is our proposed solution. So person 2 would bid along this range from 0 to V1. The problem, though, we said was that sometimes that involved overbidding. So this region over here was the probability that this proposed solution that person 2 would overbid. And we said overbidding can never be optimal. So what we're doing is we're taking that probability between V2 and V1 and are using that to bid 0 instead. Bidding 0 is safe because you know you're never going to win, but then you never pay anything either. With an all-pay auction, you pay your bid, win or lose. So you bid low, you don't pay anything. Bid 0, you don't pay anything. So that's how it improves upon this proposal. And the true optimal solution is this: when you bid 0 with that probability, and otherwise you bid it in this range from 0 to V2, so you never overbid. So that's what happens when you have 2 bidders. Now what if you have 3 or more bidders and they all have different values that they place on the item? So the paper goes on to solve that problem as well. And what they find is that the bidders with the 2 highest values should bid just like it's a 2-person auction. Person with the highest value should bid according to this rule we had earlier. Person with the second highest value should bid according to this rule. Now everyone beyond that, bidder 3, bidder 4, etc., people with lower values, they should always bid 0, it turns out. There's also some intuition behind that. The idea is that if you have a low value in the object, you're probably going to want to make low bids. But if you make low bids, you're probably going to lose a lot. If it's an all-pay auction, you still pay your bid even if you lose. So making bids that are low but still positive just isn't a good idea. So that's why people with very low values should simply drop out of the auction altogether and just bid 0 every single time. So it boils down to a 2-person auction. We already know how to solve 2-person auctions with different valuations. So it does have some interesting implications. I mentioned that one motivation for the all-pay auction is looking at competitions. So if you're on a football team and you're trained for many, many hours for a game, you don't get a refund on effort even if you lose. So it turns out if teams have different values they place on winning, that becomes an all-pay auction. It looks like only the 2 top teams should keep training and competing, and everyone else should just drop out. Let's see, I don't know a lot about sports. I don't follow it that closely. What are 2 top teams out there? Oh, football. I lived in Missouri for 4 years, so a lot of my friends were rooting for the Kansas City Chiefs in the Super Bowl. So we had the Chiefs against, I think it was the 49ers, right? So those are the top 2 teams. So they should keep training and competing and train at random. Remember, you should randomize how much you bid, how much effort you put in. The other 28 or so 29 or maybe 30 teams by now, the other teams in the NFL should just quit, according to our solution here. So that wraps up this section on all-pay auctions with different values. Come join us for our next episode, and we'll look at another example.